got exactly 4 minutes, and I made a promise to my friend. Oh, I wanted to talk about fog, but we're not going to talk about that. We're going to go, because I need to set John Roden up. John he'll get so mad at me if I don't do this. So let's go to the last couple slides here and ask the question. We skipped over some case studies, but we can talk about it. It's not a big deal. Talk offline. We saw in one of those diagrams that I showed that when water gets to the leaf, there are modifications that take place during plant transpiration. And so we want to sort of ask the question, once water gets to the leaf and transpiration is taking place, what happens to the isotope composition of leaf water, and how do we use information about the isotope composition of leaf water to ask a bunch of other questions about things that plants are doing, particularly the compounds that plants are making from where that leaf water resides, all right? And we have a model that has been developed back to Craig and Gordon that has been put in the context of leaf water, all right? Not just a body of water that's evaporating out there like we talked about earlier, but in the context of when water comes out of the soil, goes up the plant, arrives at the leaf, transpiration is taking place, the leaf is getting evaporatively enriched. The lighter isotopes are preferentially going off in the vapor phase. The liquid phase becomes heavier, and we showed that a little bit earlier. So your leaf water is isotopically heavier than the source water that it comes from. What people like John Roden and Brett Tipple are interested in is that water is the water that's in the chloroplast. That's the water that combines with the CO2 to make the sugars, the backbone of what becomes the compounds that then we might sample, like a tree ring or a biomarker of some sort, all right? And so what we need to appreciate is that once we get into the leaf, there's some additional things that we have to pay attention to in the leaf water model that will inform the other kinds of research, isotope research, that you guys are going to hear about in here. So this model here says that the isotope composition or the isotope ratio of the leaf water is going to be the function of a couple of our fractionation factors that we've already actually talked about, our equilibrium and our kinetic fractionation, our source water, what's coming up the xylem from the soil in the plant, what our atmospheric water vapor is out here, that is intermingling with the leaf. The stomata open. Most of the vapor goes off, but some of it may go back in, and it carries an isotope value with it. So you need to know what the isotope ratio of your atmospheric water vapor is. And then most importantly here, you need to know what kind of the flux is. And we characterize that by knowing something about the vapor pressure inside of the leaf. That's what EI is here. And the vapor pressure in the external atmosphere. That difference is the evaporative gradient. The larger that difference becomes, the larger the potential flux becomes, the more different the leaf isotope ratio becomes from the source water that get taken up by the roots. So we have a model here that gives us an idea that if we account for some of these things, we're going to be able to predict what that leaf water isotope ratio is. And again, that leaf water isotope ratio is what is now bathing the biosynthetic system in the leaf that's making biomarkers, that's making cellulose, sugars, the things that go into a tree ring, the things that go, some of you are going to be interested in using biomarkers to basically say something about what paleo temperatures were or other kinds of things. And so it's important that if you're working on these biomarkers like cellulose or alkanes, alkanones, the kinds of things that Brett works on, you need to incorporate how the water gets modified when it gets to the leaf and where the biosynthetic systems in that leaf are basically being bathed, all right? And this is true for leaves, it's true for microbes, it's true for animals. Seth is probably going to touch on this in his lecture. You know, you breathe, you lose isotopes, you retain others. Your body water is going to get modified in some way from the water that you drank because you're a living being and some of that's passing through you. You're excreting it, you're breathing it out. So this is basically trying to get us to think about the fact that we can understand water in the hydrologic system, but by the time we get it into the biological system, we need to understand the new modifications that water might go through. During leaf transpiration, we have a nice model. There's a model actually that's been developed for animals. There's one that's been developed by Helen Kreuziger for microbes. But this is where some of you who are interested in working on the biological compounds that get linked to the water, you'll need to go. You're going to need to understand that most of the rest of my lecture needs to have some of these caveats thrown on top of it. And what John's going to do, and I think Brett's going to do, is they're going to take this idea about changes in the water where metabolism is taking place and how it gets imprinted on the biomarkers that you guys might be interested in measuring. So I'm going to stop there because they're going to start there. And they're going to say, okay, let's start with a modified leaf water and discover how we can use it in other ways. We went through some slides here. We didn't cover everything, but you know me now. And you know where to find me. So look through your notes, and if we want to talk about specific things, we can do that. Good. Okay, thanks.